All right. So let's continue with the statistics that we had stopped at right in the last class. What was it? We had discussed mean, median, mode, and then standard deviation and variance. Right? Some metrics to understand how the data is like. So today, to continue with the discussion that we had yesterday, and just to make you understand one important aspect with regards to variance, right? Variance has two different formula to be used in a specific conditions, and I would like to draw your attention towards that. Okay, now the use cases are something like this. There are two types of variances that are used in statistics. One is called population variance, okay, and another is called sample variance. Okay, the population variance is the formula for it. I think I had shared the formula yesterday, and I'll do that once again. What is the variance formula for population variance? The general formula that we use, sigma I is equal to 1 to n, right? And then what is this? Xi minus mu whole square divided by n, right? So this was the standard formula that we used yesterday. And this formula, we use it, or this formula, if you use this formula to calculate variance, then we call this as this one, population variance. This is the formula for this, and it is denoted by sigma square. Okay. And the sample variance has a slightly different formula. It is denoted by S square. Okay. I'll tell you the difference why they are different. But right now, let's simply understand this. So this one, sigma xi, right, minus x bar or mu. I think I used mu, sorry, x bar in the last class. Yeah. Let's make it x bar. It's the same thing. X x bar whole square. The only difference that we are going to see here is instead of n, we are dividing it by n minus 1. Okay, this is called sample variance. What could be the difference, or why do we do this is the reason. Now, there are many nuances to consider to differentiate between the two, but let's keep it to the level of understanding or the level of abstraction we require for the further understanding. Okay, so population variance you consider when you have taken all the possible values in the universe. Okay, for example, if you are if your data contains all human beings, the height of all human beings, for example, then over that height data set, you can actually use population variance formula if you want to find out the variance. Okay, but generally it is not the case, right? That is why we go for, in practicality, we go for S square, sample variance. Why? Because we are picking up few people, collecting their data. Obviously, our data set will not contain the entire population on Earth. That is why we actually have to consider this formula. But what is happening here? We are simply reducing the n value by 1 in the denominator, right? What is the purpose for this? It is very simple. When you consider the entire population in reality, okay, nothing, there is no mistake or nothing is out of order. That means everything is as per the reality that is there. That is why we simply average it out using n. No issues there. But when we are taking the samples out of the entire population, then it is very likely that we have left out some variations that may exist in the actual population. For example, if I am taking in the, what is it, the height of people, if I consider the sample to be Indian population, then maybe we have something like 4.5 feet, 4 feet. If I'm considering the adults, then maybe 4 feet to 8 feet right? 8 feet is really an outlier. Maybe on an average, we can go up to 7 feet. Yeah. So let us assume we have taken this much of the samples. Indian people generally range like this. This is in our sample space. However, if you look at the world population, then the reality is that there could be some people, some abnormality who are of 3 feet, possible, and there could be some people who are actually of 8 feet, possible, right? Maybe 1 or 2%, two people in the entire world. It is possible. Some variation is left out, possibly left out, correct? So to compensate for that left out values or the spread, right, the variation from the mean value, whatever is left out, to compensate that, we actually reduce this number by 1. Okay, that is why. What does it do? It is reducing this denominator by 1 means what? The total result, whatever we get here, right? This is divided by a comparatively smaller number compared to n, right? It is subtracted by 1 means it is smaller than n, right? So it is actually amplifying the result that we generally get from this formula. This value will be a little higher, right? And that increased variance, since it doesn't actually belong to any physical sense, it is okay for us, and this exaggerated value is a safer value to consider. That is the idea. That's it for whatever we have left out in the sample space from the natural samples, right? The natural population, let's take, if from the entire world's population, if it is highly possible that we have left out some people, some variations are left out. So to be safe, let's amplify this value by what? This one, -1. This is the standard way. However, there are cases when you actually reduce this n by 2, even 3 is also taken in certain cases. Okay, just to simply to increase the variance by some factors. That's all. Okay, and that is represented by s square. So if you look at this, most of the problems that we are going to cover in our the next discussions, as well as in any practical world example, right? Generally, we are supposed to calculate s square instead of sigma square. This is a theoretical concept, sigma square. Okay, population variance is, it is impossible to collect the entire population's data. It simply will not be possible. That is why we will have to consider s square in most of the cases. However, in practice, what people do is, if the sample space is, say, for example, maybe it is covering more than 90-95% of the population, or any, for example, if I am trying to um collect some data regarding any animal, let's say, if it is considering all the animals in the planet, maybe 90-95% of it has been covered in the survey that I am doing, or the sample space is more than, say, 10,000, right, or 1 lakh, then generally the difference will not be observable. Whether you divide it by n or n minus 1, it actually doesn't make too much of a difference, because the the upper value, this value itself becomes so large, right? And dividing it by say, for example, 1000 or 999 in this case doesn't make much difference, right? So when the sample size actually increases, you can essentially use any of the formula. You must keep that in mind. So I hope this is clear for you guys. If you have any doubt, you can ask away. Is it clear or not? Shall I continue? Okay. Anya said clear, sir. Fine. Let me ask you one simple question now then. Okay. If I want to plot the marks for English subject in your college, okay, I'm collecting data about English marks, okay, in your college specifically, okay, then if I collect all of your marks, like including each and every person in the college, right, if I collect everyone's marks, then should I consider sigma square or s square sample variance? Yes. Which one should I consider? Should I go with sigma square or s square? Sigma square. Is it? Why is no one else? Okay, two people have said sigma square. One person has said sample variance. Okay, here is the thing. When you are considering all the students in your college, that is the domain of interest, right? So you are actually collecting the marks from entire population. So everyone, everyone's marks, if you are taking in, it has to be what? Population, right? Or sigma square. Say for example, I am collecting some randomly some 20 students, right? And with that, I am trying to predict the uh, predict something about the English marks. Then for this particular collection of data, I should consider what? Sample, that is S square. I hope it makes sense now. Yes? Okay. Hopefully it clarifies things. Now let's move on to the next concept called correlation. So far, whatever we have done is regarding one particular feature of data, right? Say, for example, I'm taking height or maybe simply weight or marks, whatever it is, but it is simply about one particular feature. So that particular feature, how it is distributed or what kind of trend it is following, those things we are trying to find out using the metrics that we have been discussing so far. So each mean, mode, or mean, mode, median, standard deviation, variance, right? All these things, they essentially talk about one single feature of the data, correct? But now we have to move on and we should look at another a way in which we can actually find out the relationship between two features, not just one. For example, if I have to do something like uh, I want to find out if a student getting good marks in English, right, also gets good marks in another language, say for example, Kannada. Okay, now what is this about? The relationship between English marks and Kannada marks, right? Correct? Or say, for example, if I want to find out some relationship between a person's earning and spending, are they related? How much are they related? So, if a person is earning more, does not does it say that he also spends more? Right? All these kinds of questions. What is the relationship between one person's income and his expenses? What is the relationship between a student getting good marks or a student's English marks and Kannada marks? Okay, are they both increasing or one is increasing and another is decreasing in the same manner? Is there any relationship at all? Whether they are related or they are not related, these kind of analysis if we want to do, then the metric to do that is correlation. Okay, let me write the formula, the statistical formula for it, and then we can discuss what is happening there. Okay, correlation formula, we generally call it Pearson correlation. Okay, it is given by R is equal to sigma, right, yi minus y bar. Now we have two variables, right, two features. So we are taking in two variables and then it's divided by sigma xi minus x bar whole square, right? Sigma yi minus y bar whole square. So this is the formula for correlation between two features. Okay. Now the point is, let's not worry too much about the formula because it is not required for for our requirement in this course anyway. Understanding this is quite fine, but we have a ready-made function that calculates the correlation between two features. So remembering this formula is not mandatory, but understand this part specifically. How does it calculate the correlation is the question. Okay. So what it does, say for example, xi, right? Both are under the same summation. That means what? If say for example, I have 1, 2, 3 as set 1. Okay, that is x, let's assume. And for y, I have say 5, 6, 7. Let me take this. Okay. Now, if you look at this, what happens to this term? I will take only this one. Okay. What happens to this term? It is 1 minus 2, right? Because mean value for this is x bar is equal to 2, y bar is equal to 6, right? Correct. So 1 minus 2, and then this one. What is this? 5 minus 6, plus 2 minus 2 into 6 minus 6 plus 2 minus 3 into 6 minus 7. This is what this term is going to be. Correct. Okay. Look at this. When xi is smaller than x bar, right? Here in this case, yi is also smaller than y bar. Okay. When xi changes from, so just take that. So 1 minus 2 is going to be what? Minus 1, right? Into 5 minus 6 is going to be minus 1 again. So when minus 1 is multiplied with minus 1, the negative signs, it becomes positive, right? Plus 2 minus 2, 6 minus, this one anyway becomes 0. So let's ignore that. Let's move on. 2 minus 3 is going to be what? Minus 1. Oh, sorry. This is supposed to be 3 minus 2, right? I think I made a mistake here. Xi minus x bar. So it is going to be what? 3 minus 2. And then yi minus y bar, 7 minus 6. Even though we get the same answer, the interpretation will be different here. So plus, this one is plus 1 into plus 1. Correct. So plus into plus becomes plus, minus into minus also becomes plus. So the entire term, none of the terms actually cancel out each other, or there is no decrease in the value. So these are going to be 1 plus 1 is equal to 2 divided by the divided by this term, whatever it is. Correct. Let me write it as denominator, because I don't want you to miss that part. Correct. However, if the value was something like this, y value was here 7, 6, 5. Let's assume this. Now what happens? Here 1 minus 2 is fine, but this one 7 minus 6, right? These two remain the same. Here 3 minus 2 is also correct, but this one, what is it going to be? 5 minus 6, right? Then what happens to this? This one becomes plus, and this part will become minus, right? The total term becomes what? These two, this one is minus 1, this one is minus 1. So ultimately we get minus divided by denominator. Correct? Keep that in mind. I'll tell you what this means in the later. Now let's assume, say for example, here I have something like this. I have 6 and then 7 and then, okay. What happens now? 1 minus 2, right? It is as it is. So 1 minus 2 and then 6 minus 6, right? And then 2 minus 2 is as it is, and 7 minus 6, correct? Plus, what is it? 3, yeah, 3 minus 2 multiplied with 5 minus 6, right? So this part, this becomes 0, this becomes 0, and here what is the value? 3 minus 2 is 1, 5 minus 6 is what? Minus 1, correct? So the answer is going to be minus 1 divided by some denominator, correct? Unless we calculate the value of denominator, the value will not be scaled down to a standard value. That is why, but it's okay for us. That is fine. Now we got actually three possibilities. One is x is increasing. That means y is also increasing. The first case, 1, 2, 3, right? And then 5, 6, 7. And then another case where x is increasing in the same proportion, y is actually decreasing, right? And then x is increasing, y is actually fluctuating, correct? Now, if you look at this, x is increasing, y is increasing, the correlation value something, it was plus 2 divided by some denominator, right? And then here it was minus 2 divided by denominator, and here it is minus 1 divided by denominator. Fine. Denominator is common for all because we have what? Xi minus x bar whole square. When it is squared, everything becomes positive. So the placement of these values actually doesn't affect anything, right? And these are two independent terms in the formula. That is why these two values are going to be common for everything, all these things, right? So we can simply ignore this for now, just for our analysis, right? Plus 2, we call this as positive correlation. Okay. And this is a case of what? Exactly negative correlation. Correlation exists, but in a negative manner. There is a relationship, but in the opposite direction. Here, the relationship is in the positive direction, in the sense one, if one is moving to the left, other also is moving to the left. One is moving to the right, other is also moving to the right. Or one is moving forward, other is also moving forward. But in the negative correlation, it is something like this. If x is moving to the left, then right, the y variable will try to move to the right. If x is trying to move forward, y tries to move in the backward direction. That is how the relationship is here. In this, we don't know, right? The values in between. So something we can say, when x is increasing, some decrement in y is happening, because y here 6, 7, 5, right? We don't know, not exactly. Some value is there. If we had more samples, maybe we could have drawn some conclusion, but this is how it is. Okay, we can say that plus 2 minus 2 comparatively they have a strong relation, but this one it doesn't. Okay, now let's understand the correlation in a different perspective. It is something like this. Correlation always ranges, it is a metric, right? It always ranges between a number minus 1 to plus 1. It is standardized. When you divide this value by denominator, right? Then only then you will get this scaling of the value. Fine, clear? Please keep it in mind. If we have a correlation of minus 1, it is full negative correlation. If this is the case, then it is full positive correlation. If it is in between, right, then we can say we have to decide based on the value. Make sense? Okay. Now that you have understood correlation, uh, we need to do the implementation part as well. I wanted to cover one more concept. Correlation, have you guys already learned in your statistics classes anywhere previously? You do know the graphical representation, right? For example, if I have two variables x, y, if it is x and y, then the data points, if I mark them, right, x becomes a an independent variable or whatever. Whenever there is an x and corresponding y value, if I plot them on a Cartesian plane, then if the trend is something like, if these are data points, right, something like this, then we say that it is some positive correlation. Why? Because as x is increasing, y is also increasing. That is why we are getting this kind of trend, right? And if they are something like this, instead of in this manner, if we have something like this, right? As the x value is increasing, y value is actually decreasing, right? If you draw a line, some approximation of line, then it will be like this in this direction. So this is what we call negative correlation, correct? If the data points are scattered around, like some random, right, somewhere, anywhere can be possible. If they are like this, then there is no trend that you can see. They are simply scattered around. In such situations, we say that there is no correlation between the two. Okay. And in this situation, the correlation value will be very close to or nearly equal to 0. So please remember, minus 1 does not say less correlation or no correlation. Minus 1 tells you there is a negative correlation. Okay. Plus 1 gives you positive correlation. And if there is no correlation between any two features, then the value will be close to 0. You should remember that point specifically. Okay, we will require this one later for linear regression. Fine. Shall I move forward? Okay. So one small concept that we need to understand before moving forward is called the measures for errors. Please try to understand this. I'm taking it just out of the box because seems like it is needed. Say for example, I have built something, an AI, okay, and I have a data set that contains say an X variable, and then I have a Y variable. My AI, right? For this, essentially, we have some values. Here, Y also we have some values. This is the observed data. Okay. On this data set, I have built an AI algorithm, right? It has predicted some values for the same axis. Let us say it has predicted some Y values that actually, let me call it as Y predicted. Okay. So, or I will short write it in short instead of this lengthier name. Let's call it Y cap. Okay, this is actually predicted. Fine. So individual values I can represent using yi, and individual predicted values I can represent using yi cap. Hope this is clear, right? Now the measure of errors are something that actually measure how much error my AI made in predicting the y value. So how do I have to find out? It is yi, the actual y value, minus the predicted value, right? It is pretty simple, straightforward, correct? Now, the total error is calculated something like this. There are two measures, mean absolute error, that is called MAE. Another measure is called mean squared error, that is called MSE. Okay, very straightforward. MAE is given by the formula. What is it? Sigma. We have to sum up all the errors. So yi minus yi cap. Okay. The only problem here, or only thing that we need to do with MAE, absolute errors, right? We have to take the absolute of this one. So for that, generally, how do we denote the absolute value or finding out absolute function? I can write something like this, ABS of yi minus yi cap, right? This I can write. Or we can simply write yi minus yi cap inside these parallel lines. These are also same thing, right? You can use any of the notation, and then we have to mean absolute error, right? So I have to divide this particular term by n, whatever the number of samples I have. Okay. This is what we have as mean absolute error. Now for MSE, it is going to be, what is it? Squared error. So essentially nothing but sigma yi minus yi cap squared and averaged out. Fine. That is the only difference. What are they doing? Here, say I have predicted 6 for two values. Okay. And original y was 5 here and 7 here. In that situation, in both these situations, error becomes what? Yi minus yi cap means it is minus 1 and this is plus 1, right? So if you add them up, they both result in 0. What does that tell us? The AI has made no mistake at all, which is wrong. It has made two mistakes, correct? One is in the left direction, another is in the right direction, right? One is a positive error, one is a negative error. So to find out everything, we are taking what? Absolute function. We are ignoring the sign and adding up all the errors in each observation, and then dividing those error, the sum of that error by n to get average error per observation. Fine. This is actually in the scale of errors. So it is something like this. If you make a small mistake, or if you make a mistake, if I scold you, simply scold you, then it is what? MAE. Okay. If you make a mistake and I hit you with a rod, right? Then it is what? MSE. Why? Because every error is squared. Is it? No, it is not. I can see it is coming, right? Oh, is it? No, it is. Screen is frozen. Can't you see it? Niriksha is typing something. Prarthana cannot see what I am writing now.
It's visible, sir.
Okay. Screen is not visible properly. Is it the same thing for others also? Or is it some network glitch with guys? Okay. Could be, could be. So this is it. Mean squared error amplifies the error so that the AI will correct its mistakes in an aggressive manner. And mean absolute error is like a slap or a simple scolding, right? It will not amplify the errors as it is, it will keep it. Cool. Two metrics. Somewhat similar, if you look at it, somewhat similar to variance and standard deviation, but the concept or the approach is a little bit different. Here we are taking yi, that is the actual y, and predicted y. In variance, it is about one single feature, not this one, right? How much the data is varying from the mean value we are taking in variance and standard deviation. But in here, we are taking yi, the actual dependent variable, and predicted dependent variable. Just keep this in mind. We will need it for later understandings. Cool. I wanted to cover one more concept that is called distributions. How a sample is distributed over uh, a line. Can I take few more minutes to explain that theory part and few things we can execute in the Python just to understand? Because that actually completes my stats part, whatever I wanted to discuss. Shall I go ahead and do that? Yes. Okay. Right. So the idea is very simple. We are trying to look how some values are distributed, right, in normal sense. Like if we observe, um, let's take one small example. If I am collecting the height of people, right, and I have people from maybe 5 feet. Let's just take a small sample space where 5 feet to 7 feet. I have some values. I have collected some values. Okay. Now, how these values that I have collected are distributed by count over this particular line where I am plotting 5 feet, 6 feet, 7 feet, right? Here 5.5, 6.5, right? Now, every sample that I have taken, wherever it falls, I will draw how many values, how many samples have 6 feet as value. Say, for example, 5 values, right? Now, this is the count. Okay. Now, with the number of counts, I will plot them. How many values are at 5? How many are at 7? How many are at 6? Right. This is what we call as sample distribution. How values are distributed over the range of the sample. Okay. Now, generally, in nature, if you collect the sample of entire population, right? Then generally, for example, if you are collecting the height of entire population, then the population distribution will be something like there will be some some mean value here, some central value, and around that it will be something like this, a bell shaped curve. Okay, what does that mean? More number of people have this particular height. Okay, very less and extremely less number of people will have this as the height, this value, whatever it is. Understood? Yes. And this is what we can call as normal distribution, this bell shaped curve. Okay. And the highest peak point usually comes at mu. Mu is what? Your average or mean value. Okay. One specialty about this bell shaped curve, normal distribution, is that we also have sigma square, right? Right. And square root of sigma square is what? Standard deviation sigma, correct? Mu plus sigma and mu minus sigma. If you mark these points here, say for example, the height is on an average 5 feet 4 inches, right? And then plus or minus, say I tell you plus or minus 6 inches, right? Then maybe I'm talking about sigma 6 inches, could be, right? Then the general understanding of normal distribution is that 68.27%. You can generally simply remember it as 68% is fine. You just remember this much. 68% of the values will reside between these two intervals, mu minus sigma to mu plus sigma. Okay. And if you take mu plus 2 sigma and mu minus 2 sigma, right? This range will contain approximately 95% of the values. Okay. And so on. If you continue mu minus 3 sigma and mu plus 3 sigma, right? This, if I mark it something in this manner, this will contain about 99.7% of the data. So beyond this, it is pointless to go. If we can collect this much samples, or if we consider this many samples, it is good enough. Okay, this is the normal distribution, which is naturally occurring in nature. Anything, most of the things that, for example, temperature all around the globe, or maybe temperature throughout the year, generally follows normal distribution. Okay. And like I said, weight of people, age of people, all those things, if you collect the entire population sample, then it is going to follow this one, normal distribution curve. Okay, generally this, when I say normal distribution, it is about the probability distribution. So the what does it tell you? Probability distribution means some the probability of getting some getting this height is this much. Okay, something like this. It will tell you the probability of getting, say for example, what is the probability of getting some person with height mu minus sigma. It will give you the value, something like this. It is there, but don't worry about those nuances. You just understand the curve. That is, the data should be, when plotted, there is a plot called histogram. It should follow something like this, some pattern like this. This is important. Okay. Here there are some distortions. One is called, if the data is something like this. Okay. Mu value is somewhere here. Okay. Here it is at the center. This is mu. Here we call that as left skewed. This is important. Please remember this. Okay. If there is another kind of distortion, that is called, that looks something like this. Mu value will be somewhere here. This is what we call right skewed. Okay. Means what? The sample does not contain a normally distributed sample. Maybe here it is, if some higher valued samples are more, some people with height more than 7 feet are more here, maybe, compared to people with lesser heights. Or here people with lesser heights are more, and higher heights are comparatively lesser, maybe, in the sample that I have collected. So in that situations, we say that the data is skewed. Okay. Remember this part. There is another kind of distribution that is there, that is called what is that? T distribution is also quite similar. Uniform distribution is, it is called. Uniform distribution is very simple. It looks something like this. Samples are spread equally with equal probability over the ranges. Okay. Um, any sample you pick becomes has equal probability of getting it. That kind of distribution is what we call uniform distribution. There is another called Bernoulli distribution. I will not talk about it anyway. Don't worry. Bernoulli. There is another called binomial. When you go to linear, sorry, logistic regression, right? In such situation, we will consider binomial distribution. Okay. So these are all different types, but what is important for us in this course is this one, normal distribution. Clear? So I will quickly switch my screen to the Colab. If you have any doubts, you can ask. Okay, by that time I will just unmute yourself and ask the question. Okay, I have already drawn this normal distribution curve. I'll show it to you. Yeah, it is visible, right? Is it visible? Yeah. So what I did is very simple here. Using this particular function, right? uh, I generated some random numbers. Okay, np.random function is for that. I mentioned that it should follow the normal distribution. This LOC is what the mu value is, center value, right? Scale is nothing but the standard deviation, 17. And then size, I wanted some 1 lakh samples I mentioned. That is what I got. Okay. And then I plotted them like this. If you want to see them, let me remove this. Right. Let me reduce the number of zeros. Sorry, bins. I hope you can see, right? Reduce this also, some 50 maybe. See this? So essentially what does histogram do is, this is a plot. So it divides the entire range, right? Between bins is what it is called. So every step that you can see here is a range. Okay, sorry. So in that particular range, how many samples are falling in, it it will count them and plot them in the chart. That is what histogram does. So here, for example, I have, so how many samples? 100. Scale was 17, right? Okay, I'll make it a little tighter. Size is also 1000 is too much. See this? This is what it is now. I just reduced the number of samples so that you can see the ranges a little more. So now, if you look at this, maybe if I take this particular segment, right, it could be some 2 to 3, or 0 to 20 is here, right? 0 to 10 could be here, 0 to 5. Yeah, 3 to 4. There is one sample, I guess. And that is why it has plotted something like this, right? However, for 40, maybe 40 to 41, look at this. It has some 50 plus samples, correct? Here you can see the, I hope you can make sense, right? So if I increase the number of samples, then obviously everything will change. Here bin size also I made, I had kept it a little higher. How much was it? Some 1000. Bins, number of bins 1000. Yeah. So when you generate some random samples, ideally it should merge into normal distribution. But if I simply use random, randint function is there. If you simply use it, you will not get normal curve. That is why they have written a, because computers anyway, they are deterministic machines. You will have to you can in any case it is possible to predict the values, right? So it has to work through some algorithm. When you have an algorithm, it becomes predictable, correct? So that is there. Uh, what else do I have to show you today? Okay, about the this one, right? What was it? Students. Yeah, what was the name here? Heights. Let me take the same thing. The error MSE and MAE, mean absolute error and mean squared error. I will discuss it specifically in linear regression segment. Okay, I just wanted to uh, wanted you to get introduced. That's all. So this is the array that we have. Uh, Now, if I just want you to observe one thing, NP dot what was it? Variance, right? Variance. By default, NP dot variance uses population variance. So heights is 294. Now, if you want to uh, make it or force it into sample, this one sample variance, then you should mention a a parameter called DDOF. DDOF means degree decrease in degree of freedom. Okay, n minus 1, right? That one you have to mention it here. If you mention 1 here, the formula is going to be divided by n minus 1. If you mention 2, the formula will be n minus 2. Like that, you can connect it here. So if I do this, look at this. It is 353, which is higher, right? Check. Yeah. So population variance is comparatively lesser. Why? Because the sample size itself is less. So dividing something that is less than 1, that is less by 1, is going to increase the variance value anyway. So that is the idea. We need to increase the error margin so that we are in a safe zone, right? because we are only considering some sample of the entire population. Make sense? It's a simple concept. Now we have heights. Let's take in something, say for example, weight. If I have, where is it? Where was the height variable? Hmm, yeah, it's here. Right. Weight, for weight also, let me create an array. Let's simply write some random numbers. Okay. 10, 20, 45, 30, 18, 60 was there. This, for height, I have, sorry, heights. Why do we have heights here in this manner? Let's just take it as num1 because doesn't make sense, right? Num. Okay. Let me write something, maybe 100, 400, comma 300, comma 250, comma. How many are there? 1, 2, 3, 4, 5, 6. So here we have how much? 4 already. So let's write something, maybe 50, comma 20. So num2, comma 1. Yeah, these are the two arrays. Why am I doing this? It is just to find out whether these two arrays have correlation or not. Correct? So to do that, you have, again, you have a function in this one, what, numpy. So np dot correlation coefficient between what, num1 comma num2, right? It gives you a matrix. This is what we should look at. So, or I can simply index it out, 0 comma 1. So this is the correlation that these two things actually have, the num1 and num2. Now let me change it in certain way. For 110, let me put 100, and for 20 it is actually increasing, right? Let's make it, say for example, 200, and then for 45 let's make it 4500, sorry, 450, right? I'm following the same trend in a slightly scaled manner. Okay, for 30 let me make it 300 again, and then for 18, 180, and for 60 let me make it 600. Now let's calculate the correlation. Look at this. The correlation value is coming towards 1, right? 0.99999, following the same trend, just in a different scale, right? They have a linkage. So right now, if you look at this, when I'm trying to build my model for prediction, having any one of these is sufficient enough, right? Because anyway, this is following this particular trend, correct? So what is the point of having two things doing the same job when one can handle it properly, right? That is the idea behind. Actually, that is the relevance of finding out the correlation. Now let's simply do this in a reverse manner. Slice it out. It works. I don't know. It does. Yeah. Now look at the two arrays. 600, right? 180, 300, 450, 200, 100. It is in the reverse order. I have simply reversed the list here, right? That is why the correlation has turned out to be minus 0.5439. Please don't expect it to be minus 0.999. Why? Because it is not in exactly linear, right? Here 1, 10, 20, 45, 30, and then 18 and 60 is there. So since num1 and num2 both are not exactly linear, some variation will be there, because here calculate the coefficient, it is going to be exactly 1, right? And then if you reverse this, what is going to happen? Pretty straightforward. You are going to get minus 0.9777, very close to 1 as well. This value difference could be 0.03 or 0.02 difference is generally because of the floating point inaccuracy that is present in Python. Okay, this is how it is, the correlation. However, if the values are some 700, or there is no uh, relationship at all, in that situation it could be, if you look at this, there is a correlation of 0.404, which is less than even 50.5. So if I make some 10, yeah, so it is not at all following this trend. The values are everywhere. That is why you are getting what, 0.078, which means what, close to zero, hardly any correlation. Fine. If you have any doubts regarding this, you can ask away. Otherwise, we will wind up. So as far as today's session is concerned, it was more like covering very the more of the abstract concepts. One was correlation, obviously. Another was the sample variance and population variance difference, and then different kinds of distributions, especially the normal distribution that we have discussed, right? Apart from that, few concepts about errors, two different metrics about errors, MAE, mean absolute error, and mean squared error. What is the relevance of those metrics? We will discuss when we discuss linear regression. Okay, so I'll stop sharing now. If you have any doubts, you can just ask.